Yep. All right. Good afternoon, everyone. It's great to see everyone's faces, to be in the classroom. Well, you all made it. So did I. Let's hope you all make it out. I'm mostly over the contagious phase. So we'll well, we'll find out next week, depending on what happens with the people in the front row. No, I mean, I'm tested negative for COVID. Okay. First things first, I noticed something today, and well, yeah, 201. See, that's not that's that's a perfect beginning, right? Detail oriented. If you ever look at your any job application, they'll say they want team people who can work in a team. They can also work with individuals, and detail oriented is part of it. Well, until this morning, we were all working in 2021, and everyone missed it across all three of my classes. It was not intentional. I mean, even I overlooked it. I missed it too. So this is something I noticed this morning. So anyway, we are now firmly in the present in 2022. All right, let's see. 321. Let's switch over. The recording is on. Still in 201. And yeah, that's okay. It wasn't too much of the time. It's fine. All right, content library, determining operating mode. For those of you taking the lab, I guess it's pretty old. All right, common emitter amplifier load line analysis, right? This is what we're going to look at today. I may bring up my notes. All right. Okay. Share. And one note. Online students, can you all see the slide? Well, hopefully you can. All right, I got a thumbs up. Yes, got a thumbs up. So, load line analysis. Before we begin that, I wanted to just recap the input and output characteristic of a common emitter amplifier, right? So, common emitter amplifier is because the emitter terminal is common to the input side as well as the output side, hence the common emitter, right? The other configurations are common base and common collector, but common emitter is by far the most popular one. So again, in this class, we'll only look at the common emitter. We will not look at the other configurations. EE students who spend like an entire academic year studying these circuits, they look at, well, all configurations. All right, CE amplifier. This is the input side on the left, right? So it's the base emitter junction. This is the output side, which is the collector emitter junction, right? Here you have the AC input. This is the DC bias voltage, VBB. On the right, we have the VCC, which is the biasing voltage. And then the output is taken across the collector, from the collector to ground. Okay. On the left here is the input characteristic. Basically, it shows you how the voltage and current relation, how the voltage and current behave on the input side. And so it's showing you a curve of VBE, which is the base emitter voltage versus the base current IB. And because it's a forward bias PN junction, it looks like a PN junction characteristic, right? It looks like a diode characteristic, meaning there is no current flowing through that junction until that the depletion layer barrier is overcome. The threshold voltage for a silicon diode would be around 0.6. And so the input characteristic is something you have seen before, the first chapter, right? It simply looks like a diode. Output characteristic, a little bit different. If you think of it, it's kind of this characteristic on its side and flipped. Not exactly like a forward bias PN junction, but we've seen earlier how a transistor functions, right? You have the input junction, base emitter junction, forward bias, and the collector emitter junction, reverse bias, right? This is an NPN transistor. So this is still forward bias. And this right here, collector emitter, is still reverse bias, right? And because of that, we have these kind of characteristic curves, meaning there is a certain amount of current that will flow through the transistor. And then once that threshold is crossed over, it's almost a flat line. The voltage will increase dramatically, but the current at the output will remain constant. So this is a graph of VCE, the collector to emitter voltage right here, VCE, versus the collector current IC. All right, so you can see for every single value of IB, there is a output amplification in IC. So if you take a look at just the first one, this, no, they didn't. So these are all values for IB, meaning there are a set of curves on the output side. For every, yeah, no, I'm not going to bother with it now. Anyway, for every given input in IB, every change in input in IB, you have a set of curves. So all of these values, IB goes from 10 microamps to 50 microamps. So for every value of IB, you can have a different set of curves, different set of data points. Okay. I don't know if students did this in 361. You haven't, right? So like there's an experiment in the E major labs where the E students actually generate these curves. They generate the data. So they apply different values of IB and they measure the VCE versus IC and create a chart that looks exactly like this. Anyway, so for every set of IB, you can see the corresponding value of the collector current. Okay. And right here, you can see input side, which is IB, output, which is IC. And of course, this is an ideal characteristic that is shown in this diagram right here. If IB, for instance, is 10 microamps, IC is coming out as 1 milliamp. Amplified, amplification factor. So just from the characteristic, we can predict that this is working as an amplifier. And if I wanted to find IC or IB, that would be what, 1000 divided by 10, so 100. And this, of course, is the transistor amplification factor beta, the current gain. So it is possible to determine the transistor gain or the current gain from the characteristic, right? IC is beta times IB. And so you can take a look at both the characteristic and determine the beta. Anyway, so there's lots of things that we actually do in analysis, but for 321, typically I just like to just introduce this topic, show the curves, and show the input and the output, and then we move on to the load line analysis. But does all of this make sense? Right? We have the input characteristic, looks like a diode characteristic, and the output characteristic where you have almost constant current, constant output current for a huge increase in the output voltage. Okay. All right. So let's see how we can perform a load line analysis on a CE amplifier. Now, if you remember, again, because the last few classes we've not been here, amplification, what did I say? We have a very small AC signal that is input into an amplifier circuit, and the amplifier circuit imparts a much higher value to that input AC signal, right? But the power to do so comes from the applied DC biasing voltages. So if you'll remember, I had this kind of layout. You have a small AC signal, and you have a large DC voltage. So small AC plus large DC gives us a large AC. And that is what we're going to study here, right? So since the AC input signals are small, if we analyze the transistor operation just for those AC signals, we say it is a small signal analysis. And if you analyze it just for the DC biasing conditions, we call it a large signal analysis. Okay, and the transistor behaves differently for both. So small signal analysis and large signal analysis both have different kind of equivalent circuit models that we can use to analyze the circuit. But an amplifier essentially is taking a small AC signal, combining it or obtaining the power from a large DC voltage biasing circuit, and then imparts the same energy, same power to that AC signal. And so we'll perform the analysis. I will use the input and the output characteristic, and we'll show you how exactly it functions. Okay, so let's begin. Okay, so first let's tackle the input side. Okay, so there will be load lines for both input and the output side. So on the input side, we have 4 voltages. So if you apply KVL to generate an equation, and I typically always start at the bottom left corner. So KVL, let's write down input side, apply KVL, and I have 4 voltages. Starting at the bottom left corner, I have minus V in plus IB times RB, the voltage drop across that base resistor, plus VBE, the base emitter voltage, and minus VBB. Okay, minus VBB. So and it all sums up to 0. All sums up to 0. So if I was to generate this equation, rearranging the terms, I would get IB RB plus VBE is equal to VBB plus VN. Right? Let's take a 10-second pause. Let me know if you have any questions. We good so far? Right, now the two quantities we are looking at are VBE and IB, right? X-axis and Y-axis. So to find the 2 points, the constraints on the graph, on the characteristic, we said either each one of them 0 in its turn. So first, if we set IB is equal to 0, meaning on the x-axis, the farthest point, you would get VBE is equal to VBB plus Vin. Right? So you get the first point on the x-axis when IB, or the y-axis point, is equal to 0. And then in turn, we set VBE equal to 0. And then you get a value for IB. The value for IB would be VBB plus Vin over RB. And that is basically shown here, right? So when y-axis is equal to 0, x-axis point is VBE plus Vin. When x-axis is 0, y-axis point is VBB plus Vin over RB. And those 2 points are the constraints on the transistor amplifier placed by the biasing voltages, right? Those are the constraints. And as usual, the intersection point gives us the quiescent point, the Q point of the amplifier. Q point of the amplifier. So if you take this point as x1, y1, and this point as x2, y2, here y1 is 0, here x2 is equal to 0. Find the slope of the line. M is equal to y2 minus y1 divided by x2 minus x1. You basically get this point right here, y2 divided by minus VBE plus Vin. So slope of the line, of this line, again, slope x2 minus x1, and you plug in these values, and you obtain minus 1 over RB, which of course makes sense. It's a descending line as the value increases, so the slope is negative, but the slope remains constant as minus 1 over RB. And this is important to remember, that the line slope does not change, and it's not dependent on Vin or VBB. The slope of the line is only dependent on the base resistor, RB. That's it. So depending on the value of that resistor, that line, you can design that line to be anything. It only needs one quantity, just RB. That's it. Doesn't depend on anything else. So when Vin of t changes, the line position might change, but the slope does not change. So it's still going to be the exact same slope depending on what the component value is. Does that make sense? Take 10 seconds, think about it. Let me know if anyone has any questions. Again, we're looking at the input side. Looking at the input side. All good? All right, I think some people are still thinking. Okay. Now, one point about the intersection, one note. The intersection point, as I said, would give you the Q point. But that intersection point is valid when Vin is equal to 0. Remember, Vin is this, Vin of t, a time varying AC signal, meaning its value is changing with respect to time, right? Constantly. So it might go to a positive peak, come back to 0, goes to a negative peak, come back to 0, positive, negative, positive, negative. So it's time varying. the sounds that I'm making right now when I'm speaking, the microphone takes it, converts it, right? So it's a time varying AC signal. So if we were to connect this microphone to a oscilloscope, you'll be able to see, well, a time varying signal, sinusoidal signal. So when it goes to 0, the load line is right here. When it goes positive, it's going to shift up. If it goes negative, it's going to shift down. Right? When Vin increases, this is going to go up. When Vin decreases, it's going to go down. The slope still remains the same. But depending on the value of Vin, that line shifts up and down on this characteristic right there, on the input characteristic of that base emitter junction. And so the value of IB changes. VBE does not change a lot, but IB changes a lot. And when I say a lot, well, it's all in microamps. So if you think about it, VBE is in volts. IB typically would be in microamps, very, very small number. And this is a big change in that input load line, but the change in VBE is like minimal, right? Very small change. But the change in IB right here is much higher or much larger. You keep that in mind when we go to the output side. Okay, so Vin of t, when Vin of t changes, the position of the load line changes, and the position of the load line changes, there is a very small change in VBE. Again, because it's a forward bias PN junction, so very small change, but there's a correspondingly large change in IB. Now, again, when I say large, it's a few microamps. But if you're talking about 5 microamps and then goes to 10 microamps, it's double. 5 microamps, it's incredibly small current. You cannot even measure it just directly. It's very small current, but effectively, it's still doubling the amount of current. Does that make sense? Okay, it's crucial to understand this before we understand the output side. Any questions? Okay, so now let's go to the output side. With the exact same procedure, we write the KVL expression on the output side. And on the output side, we now have 3 voltages. We have VCE. So I start at the bottom left corner of the loop. I have the collector to emitter voltage drop across RC, and my biasing voltage VCC. 3 voltages. And so on the output side, I can write, let me write it on this side right here. Output side KVL, I get minus VCE minus IC times RC. The IC is coming from the top, right? So it's coming from the top. It's minus on the bottom, plus up top, plus VCC is equal to 0. If I rearrange the terms, I get VCC. Actually, let's write it this way. I get VCE plus ICRC equals VCC. To find the constraints placed on the circuit, we plug in IC is equal to 0, and we plug in VCE is equal to 0 to find the other corresponding value. So when IC is equal to 0, you get VCE is equal to VCC. And when VCE is equal to 0, we get IC is equal to VCC over RC. And when you plot those 2 points, you get this load line right there, shown in characteristic in figure B. Okay. So you get this load line right there. Make sense? So now take a look at the equations, the 4 equations. We have IB is equal to VBB plus VN over RB. If VN is equal to 0, it's VBB over RB, right? So if you have a time varying signal, it goes to 0 after going to a positive peak and returns back to 0 after going through a negative peak. So at that point, zeros, VBB over RB is at the center point. So IB is equal to 0 at that point. Now, as Vn increases, I want to keep both of these. Actually, slope is not important, so it's fine. The equations and the graph. As Vn increases, what happens to IB? There's some murmuring. What happens? So look at the equation. If Vn increases, what happens to IB? It increases. If Vn decreases or goes negative, IB decreases, right? So we go to the input side, as I was saying. If Vn increases, this increases, so IB increases. If Vn decreases, IB goes down. So the load line shifts up and it shifts down, right? This is VBE versus IB. Come to the output side. When you come to the output side, you have IB values, different values. If IB increases, what happens to IC? IC is directly proportional, it's beta IB, right? So if IB increases, IC increases, multiplied by the current gain factor beta, 100 times or 200 times or whatever the value is. So IC increases, but what happens to VCE? VCE decreases, right? So as you increase the load line, you're moving the point towards the left. And when you're moving it towards the left, your VCE is decreasing. So the voltage in VCE starts getting smaller. Okay, starts getting smaller. And so I like to use this chart to explain how that works. So, oh, I need space on the left. I need to move this. Let's move it to the right a bit and maybe a little bit down. I probably need a few more lines in there, but let's see. And this is approximate. This is 5. Let's call this 15. Yeah, 25, 35, and 45. These are all values for IB, right? Different set of curves. So now we take IB from the input side, and let's say our Q point was, let's say it was somewhere here, right? So when Vn of t is equal to 0, that's our Q point, center. So let's change the color right there. This is my Vn, okay, Vn. So Vn of t, this is of course when it's 0. This is when it's max, and this is when it's minimum. Well, it's Vn of t, but it's showing the base current IB. Okay, graph of IB. But that's the input signal that's going in. All right, so superimposed on the characteristics of the output. So graphically, if I wanted to find the output, let's look at what happens to IC. IC is going to be, well, because it intersects here, that's my intersection point. That's the other intersection point, so 0 is right there. And well, let's just say it approximates and it's over here, somewhere here. And so my IC increases or comes out in the same phase as my input IB, right? So when each of these points increases, my corresponding IC is also increasing. And when it decreases, IC also decreases. And mathematically from the equation, we already know IC is equal to beta times IB. So that's all well and good because that's rather straightforward. We don't have to. This is IC. Okay. And IC is varying from, and this is going to be approximate. So there are no values on here. But I'm just assuming this was around 10 milliamps, and this would go to around 30 milliamps. Okay, so it goes from 10 to 30 milliamps. But now let's look at the output side. Okay, on the output side, didn't have to move it that far to the right end after all. All right, but messed it up. Okay. Obviously, my drawing leaves a bit to be desired, but at 0, it's quite easy to see what happens to VCE, right? It's right here, whatever that intersection point is. Maximum intersects here, and my output goes here. What is this value? This value is lower than the center point, right? So as IB goes max, VCE goes minimum. And when IB goes maximum, when IB goes minimum, VCE goes maximum. X-axis, right? 0 is here on the left, max is on the right. So if you move towards that way, your VCE is decreasing. If you move towards the right, your VCE is increasing. So when IB increases, your VCE decreases. So as IB increases, output VCE decreases. And so what you get is this. (180 degrees out of phase with the input. And so this works as an amplifier, but it is also an inverting amplifier at the same time. It was inverting the phase by 180 degrees. So a CE amplifier works. CE amplifier circuit is amplifying the input signal but it is imparting a 180-degree phase shift to the output. Does all of this make sense? Graphical analysis. I mean, there's a lot more. I mean, in EE, and I keep repeating the same thing, right? There's a whole lot more to the analysis. There's like, when we get to like graduate level, E majors can actually look at transport phenomena and see how the electrons and the holes are actually moving inside, the charge carriers are moving inside the circuit. And there's so much analysis, so many equations that you can use. This is just the bare basics, right? And in your own fields, as you go higher up in your own major fields, you would specialize and analyze engineering problems in minor detail, right? So without going into too much device physics, without going into too much equations, I want to make sure students understand how and why this works as an amplifier. So let's take a pause, think over it. Let me know if you have any questions. Does everyone see how and why it's an inverting amplifier? Let's see, how much time do we have? 1:47. Yes, question? Okay. Yes. So this would be VCE. This would be VCE minimum. This would be VCE maximum. And this point, what is this point? VCEQ, the Q point. So the Q point of the output characteristic on the output side, VCEQ. So the center point here is IBQ. This is IB max. So this would be IB max. This right here in the center is IBQ. And this is IB minimum. And IC correspondingly at the same time as IB. But VCE, the upper voltage, is inverse. Make sense? All right, let's look at an example. So we are given the input characteristic and we are given the output characteristic. And we are asked to find the 3 points for VCE. So VCE max, min, and Q point. All right, Q point. We are given that VCC is 10 volts. All right, we are given that VCC is 10 volts. Oh, come on, minimum and Q point. BBB is 1.6. RB, base resistor, is 40 kilo ohm, and collector resistor RC is 2 kilo ohms. Okay. V in of T, the input voltage, is given as 0.4 sine of 2000 pi T volts. Chapter 5, AC analysis. You want to remember? V in of T is Vm sine omega T plus or minus theta. Vm or Vp is 0.4. The reason I'm pointing this out is because V in max is 0.4 and V in min or minimum is minus 0.4. Okay. So it shows you only one peak. If you compare it, Vm sine omega T plus theta, VM or VP, one peak is 0.4. So Vin max is plus 0.4 volts and Vin minimum is minus 0.4 volts. That's the swing, plus minus 0.4. Okay, so let's analyze this. On the input side, we have our equation from the load line. Now it's the same circuit that was previously, so we can just reuse those equations. And those equations, the point on the right for load line, for plotting the load line, VBB plus Vin, right, on the x-axis. So that gives me 1.6 plus 0.4, 2 volts. And then if Vin is 0, actually, point is this. Vin is equal to plus 0.4, 0, and minus 0.4. All right. So the three values that VBB plus Vin would take is 2 volts, 1.6 plus 0.4, 1.6 volts, and 1.6 minus 0.4, so 1.2 volts, which are the 3 points that we have here. Okay, so for each line, we need a point on the x-axis, right? The equation is still the same, VBB plus Vin. Then on the other side, on the y-axis, IB is VBB plus Vin over RB. Again, Vin has 3 points, and so I get IB as, what do I get first? 2 volts divided by 40K. So that gives me 50 microamps. And then the second one at 0 would be 40 microamps. And 30 microamps. And those are the 3 points right here. So again, load line analysis, we take our equations and we substitute y is equal to 0. We obtain the 3 points on the x-axis. Then we substitute x is equal to 0 and you obtain the 3 points on the y-axis. Right? Join those points, you got your 3 lines. Your 3 lines are telling you or showing you the variation in Vin, the variation in IB that is caused due to the Vin. So IB is going to vary from this point, this intersection point, all the way up here, that intersection point. Okay, so the intersection points is showing you where IB changes because of the applied Vin. Makes sense to everyone? And those intersection points, approximate values are 15, 25, and 35 microamps. Okay, so once you have plotted the load line, you want to find the intersection points. The 3 intersection points gives you the variation in IB due to the change in Vin. Vin, of course, being our signal going from plus 0.4 to minus 0.4. You good so far? So if you analyze the input side, we have our 3 values for IB, which is 15, 25, and 35. Now we go to the output side. And on the output side, again, you do the same thing for load line. Plug in y is equal to 0. So you get the x-axis value as VCC is equal to 10 volts. Plug in x is equal to 0, and you get the y-axis as 5 milliamps. Okay, 5 milliamps. So you have the load line values from here. So plot load line. Find the 3 intersection points for each one of the characteristics from the input side. The input side, we had the 3 points, right? IB was equal to 15, 25, and 35 microamps. So 15 is here, 25 is here, 35 is here. We take the intersection points of the load line with those characteristic curves. And that gives us the value of VCE min, VCE max, and then VCE at the Q point. So the intersection points right here VCE. When IB is max, we get VCE min. So IB max gives us VCE min, which is approximately equal to 3 volts. IB min gives us VCE max, which is around 7 volts, and IB Q point or quiescent gives us VCEQ, which is around 5 volts. Okay, 5 volts. We have a couple of minutes left. So this is the graphical and mathematical analysis. Now, think back to the input. V in of T, oops, sorry. V in of T varied between plus and minus 0.4. So the total variation is 0.8 volts. And now look at V out. The total variation in V out goes from 3 to 7, 4 volts. So total variation here is 4 volts. So your V in was 0.8 volts, your output voltage is now 4 volts. So the effect that the amplifier has on the input signal is defined as the gain of that amplifier. And gain is simply a ratio of the output voltage to the input voltage, V out over V in. So for this amplifier, we can calculate the gain as simply V out over V in, 4 over 0.8, basically 5. And because it's an inverting amplifier, we can place a minus in front of it. Inverting amplifier. Make sense? So think over it. Let me know if you have any questions. So V out is basically this, VCE. VCE. So this is 7 minus 3 volts. 7 minus 3. So output is the VCE voltage, collector to emitter voltage. One final point about this, and I think it's 2 o'clock, so we'll just take 30 seconds. Well, students still have other classes, right? So in this input goes to the output. So 0.8 volts is now 4 volts. So total gain is 5. And it's inverted, so it's minus 5. But if your V in was very large to begin with, if your V in was, let's say, 1 volt, 1 volt, so the total variation is plus minus 1 volt, meaning 2 volts. What happens? You are no longer within the characteristic of the amplifier. You might be doing something like this. So if your V in is something like this, which is very, very large, your output might go somewhere here. And so you would get cut off. And when you get cut off, this is what happens. There is clipping at the top and the bottom of your waveform because the input signal is too large. It's driving the it's driving the transistor into cutoff region in the negative side. It's driving it into the saturation region on the positive side. In both cases, it is causing a distortion, right? And that is what happens when you turn the volume up too loud on your speakers, your amplifier, your signals coming in, amplifier is amplifying it too much, and the top gets cut off, so your speaker sounds distorted. And that is basically what's happening. It gets clipped at the top and the bottom. Okay, at the bottom it's driving it into cutoff, at the top is driving it into saturation. All right, so we'll end class here today. We'll have a quiz on Monday. BJT fundamentals. Load line analysis, maybe some basics, but not too much in detail. All right, I'll have a homework. The homework will have an extra credit tutorial, but it's not going to have, I'm not going to make it due on Sunday night. I'll have it extended to like Tuesday or Wednesday. So you have time enough to study it and then do a good job on it. All right, have a good weekend. And if you have any questions, I'll be available in my office. I just have one quick question. Yeah. How come when you find your IP values,